So, how do we make it so that more people can engage with self-driving cars without working for Google or Waymo or whatever? And the answer is you take the essence and you reduce it to a unit that anybody can have access to, exactly as we did with drones. I didn't have a Predator, so I made one out of Lego and foam. And I didn't have a self-driving car, so I made one out of toy parts and a Raspberry Pi. And so what you're seeing is this incredible diversity of people who are engaged.
You're listening to Gradient Descent, a show about machine learning in the real world, and I'm your host, Lucas Bewald. I knew Chris originally, or knew of Chris, as the chief editor of Wired and the author of The Long Tail. But it turns out that in the last decade, he's gotten super into drones and started a company around DIY drones, and now works on 3D robotics and DIY robot racing. So it's a super interesting conversation, and I think you'll enjoy it.
Chris, it's such an honor to meet you, and you have such an interesting kind of arc to your career. Before we get into the stuff you're doing now, could you kind of tell us about the highlights of what you've done before the robot stuff?
Sure. It looks really chaotic and random, but like every step made sense at the time, and possibly if I do my job here, I can make it make sense in retrospect. So, I was a terrible student, essentially failed out of high school, then failed out of college, then played in punk rock bands for most of my 20s working as a bicycle messenger.
Wait, is that right? Wait,
yeah.
Really?
Yeah. I mean, the best story is that I was in R.E.M.
No, wait, really?
Well, there's a little bit of a footnote to that,
okay,
which is not the R.E.M. No, I was in a band called R.E.M. in Washington, D.C. We were really good. We were, about to release our first album, and our manager said, it's the weirdest damn thing. There's this other band called R.E.M., but, they're releasing their album on the same day. But don't worry, they're from Athens, Georgia. How good could they be? And so we thought it would be really funny that, we, the sort of the famous, big city R.E.M. would invite the little country R.E.M. up to Washington, D.C. for a battle of the R.E.M.s, and the winner would get to rename the loser, which they agreed to. And they came up, and we played a joint record launch party.
Wait, so this is like early 80s, right?
Yeah, I guess it was about 83-ish.
83?
Maybe 85-ish or something like that. And so we had the famous 930 Club in Washington, D.C. So we played, and we flipped a coin to see who goes first. We went first, and, we played a good set. We got decent applause. We went to the bar to celebrate our inevitable victory. Then they came on second, and their first song was Radio Free Europe, which was their first single.
Yeah.
And our jaws were on the floor, and we're like, our beer's unfinished, and we realized we were completely sunk. And, they were great, as you might imagine. Won, as you might imagine. And Mike Mills, the bass player, stayed around just long enough to rename us Egoslavia because we were so arrogant to think that we would win. And we released our album under that name, and the rest is history.
Wow,
anyway,
that's amazing.
Yeah, so it's that was my little sort of brush with fame. But yeah, so complete fuck up. Student, sorry, we may have to beat that. But eventually in my late 20s, I was like, this. I don't think this punk rock thing is really working out for me. I should probably use my brain again. And as a teenager, I'd been sort of thrilled by physics, and I got the Feynman lectures on my 16th birthday, which was like I read those instead of going to school. And so I went back to college, and I decided at this point I had so much to prove that I was going to do the hardest thing possible, which was physics. And so I got a degree in computational physics, which was a new thing at the time. And the job of all of us physicists in those days was basically to understand the nature of matter as we go closer and closer to the Big Bang. So higher and higher energies. And that means bigger and bigger and more expensive particle accelerators. And we were all sort of queued up to work on something called the superconducting supercollider, which was going to be in Texas. And the problem is that the cost of the collider kind of scales with the energy it produces, and went from 8 billion to 16 billion to 19 billion, and then Congress canceled it. And that was it. There were just, there were no more interesting experimental facilities in the United States, and it was all going to be kind of queuing up for CERN, the LHC, and CERN in Switzerland. And I realized I could see my career. I was going to be like an assistant professor at Iowa State, waiting for my experiment to run at CERN, and 20 years later it would run and it would probably fail, and I would be author 300 on a paper about a experimental failure, and I was like, that sucks. And I wasn't even very good at it. So it was time to move on. And so I went to the adjacent space, which was the science journals, Nature and Science, to write about science rather than be a scientist. And then, went from there to The Economist to lead their tech coverage. One of the things that we learned from that generation of physicists who just, basically their careers vaporized with the SSC, was that although physics was not going to be our future, we had accidentally created the internet, as physicists. So the internet, as you know, was created largely to link research facilities. The web was created at CERN, a physics lab, and we as physicists had the only big data out there. We were the only people doing big data because we had all this data coming from the particle accelerator. So we had these skills, big data and internet. And so when this generation, vaporized to the winds, most of them went to Wall Street to become quants, which was the next source of big data. And then some, the ones who didn't do that went to sort of, create the emerging internet industry, which is kind of what I did as a writer, and, sort of kind of move media onto the internet.
Before you go further, I just, like getting a PhD in quantum physics is no joke. Like, I think, I have a lot of friends who feel kind of stuck in academia and have trouble getting out, even though the careers available to physicists, for example, are quite good. I think most people feel a little bit like failures because, like, inside of it, you're so like funneled through this escalator to success. I mean, you speak so rationally about it, but actually I feel like most people aren't able to make that leap. Do you think it was like your perspective of having, not jumped from undergrad to grad school, or something else?
Yeah, I mean, so to be clear, I don't have a PhD. I dropped out of the PhD program, not even an ABD. I didn't even get that far. But if you love physics, it's kind of heartbreaking to see what's happening now. So you're inspired by the greats, but like all scientific disciplines, you need theory and experiment to be matched by a sort of a limited amount of time. So a theory comes out, and you want the experiment to be able to kind of falsify or not within, say, 5 years. If that gap grows, then theory becomes unmoored in reality, and it becomes almost like poetry. And and now it's like the coolest theories and the ones that sort of are best told are the ones that spark the imagination, and it's almost like metaphysics. No, it's no longer physics. It's almost philosophy. And that's a really weird place for a scientific discipline to be. And I think that the people who stick with it, and all they can really do, they can either line up for an experimental facility and see you in a generation, or they can go into theory, and it's seductive in that it's math, but it's not real. And I think you can really get lost there. It's almost religious. There is a slight ray of hope, though, in cosmology, in that rather than having physics facilities, on terrestrial physics facilities, that we use the stars as to create energies and to observe them. And so we're getting much better at using astrophysics as an experiment, but it can't do everything. So I mean, I'm not sure I answered your question, but basically, if you fall in love with physics, what you get is a really good grounding in statistics and math, but it's not a great career. And it's probably best to use that grounding, and there's plenty of physicists out there doing good work in machine learning elsewhere. And so that's why my degree was actually computational physics, which in retrospect was more about compute than it was physics.
I see. Interesting. And so then you sort of left that whole thing to be a journalist.
Well, yeah. I mean, again, it was sort of stepwise. My parents were journalists, so it was kind of like the one thing I was sure I was not going to do was journalism. But I went, writing about it but again, your Science and Nature are scientific journals, so it felt wasn't like grubby newspapers. And then The Economist, again, a lot everybody was a PhD of one sort or another, or most people were, and so it really felt like you were part of like extended academia. Then moving to Wired, and to take over Wired in 2001. That was the first leap into traditional media, owned by Condé Nast, which owns like Vanity Fair and New Yorker and things like that. So traditional media, but they bought Wired. They hadn't created it, and Wired was created largely as as an evangelical Bible of the emerging internet. And one of the reasons I left science was because, in '93, when Wired was launched and the internet was just forming, I wasn't sure what it was. I mean, again, we thought it was just like a way to telnet into the cray at Los Alamos. We didn't, and then this magazine comes out with these day glow colors saying, no, this is a cultural revolution. This is going to change the world. This is going to change everything. And it just blew my mind. I suddenly realized that this thing I was kind of good at actually had these big implications, and that had dictated the direction of my career. And so when the opportunity came to lead it, I was like, yeah, this is the religion I believe in.
Oh, that's funny because
yeah,
2001 is a really interesting year, right? Was this pre kind of bubble collapse or post
no,
bubble collapse?
post. It was like the best and the worst time. So the bubble collapsed in March of 2000.
Oh, 2000.
Yeah,
Got it.
and
Right.
and so at that point, the most of the world was saying this is a subprime mortgage. This is a a hoax, perhaps
Right.
even worse. But you had to believe that the internet was not the stock market. That there was something real at the core of the stock market, and that the bubble was a finance artifact, but the underlying trends were real. And it was very unpopular and somewhat minority view at the time that the internet was real. But if you were to bet at that time, as I did, that the internet was real and the stock market thing was the stock market thing, then you're buying at the bottom, essentially. So I don't think I would have been offered the opportunity to take over Wired if everybody knew it was the hot place to be, and I wouldn't have been able to hire the people I did. And as I say, the best time to take over when you're like not particularly experienced at this kind of stuff is at the bottom, because you can hire people. Your lack of success is cloaked by the market's lack of success. It's impossible to succeed in that environment, so no one can tell whether your failures are yours or exogenous ones. And then thirdly, once things start to pick up again, your year-on-year growth looks amazing. So it worked out really well, but it was a very counter cyclical bet at the time. And if you look back at underlying internet adoption trends, you almost can't see the bubble bursting. It was really isolated to the stock market, and all that capital created a huge amount of infrastructure, which we still enjoy today.
Interesting. So what about the long tail? Like, how did that kind of come about? And
yeah, so thank you. So when you take a physicist basically by heart and you stick them in media, I'm not trained as a writer or as an editor, or didn't have any particular interest in media. I was really interested in the story, but I'm a nerd. So what am I going to do is I'm going to try to do research about this story. And so not trained as a journalist, I was trained as a data analyst. And so I was like, well, something important is going on, in the server farms of, Amazon and Netflix. We can probably see it as a lens on human behavior in a way that we never had before. We're basically instrumenting, society in a way we never had before. And this is obvious today, but it wasn't at the time. And I said, I bet if I could get that data to see how consumer preference actually looked at scale, I bet it would be interesting. I bet we'd learn things that we weren't seeing, with the, I don't know, Department of Commerce reports or, the Walmart quarterly earnings.
Mm-hmm.
And so I asked. And so I just started. I asked the Yahoos and the Netflixes and the Amazons, for their data, and weirdly, they, had to sign a couple of NDAs and anonymize some stuff, but they gave it to me. And I just got these massive data sets, and I did really dumb stuff. I just stuck it into a spreadsheet. And you have basically sales of the set of products. Take music, for example. You get like 1 million tracks, and then you rank them in terms of popularity. And I just stuck them in a spreadsheet, and nothing showed up. It's like the graph was empty. And I was like, wait, what happened here? And I said, well, let me just cut off the first 100 and just graph from like 101 down to 1 million. And then I could see the line, and I realized what happened is that the inequity of the marketplace, the incredible scale differences between the number 1 track and the number 1 million track, it basically compressed my scales. So the scales are set by the number 1. The Y is set by the number 1, and the X is set by the number million. And so the line was basically just right along the axes. And until you cut off the head, you couldn't see the tail. And it was simply that dumb thing that I did, one night with a spreadsheet that kind of created this, that just shifted my gaze to the right. And I realized there was a lot there that we weren't paying attention to because it was, high high number, but low magnitude. And that created the notion of the long tail. And then, it got to other data sets, and they all confirmed that if you kind of, if you have basically infinite inventory and mechanisms for people to explore that inventory, that consumer preference shifts down the tail. Now, not entirely. We still have network effects and hits and things like that. But basically, there was a lot of suppressed preference for niche stuff that was suppressed by the, scarcity function of shelf space that was opened up by the non-scarcity, by the abundance of online, databases and e-commerce, et cetera. What's interesting is the caveat to that story is that I got a bunch of data sets, and then about a year later, AOL was also sharing some data and shared with some academics, and somebody figured out that you could de-anonymize.
Oh, the search data.
The search data. They could
I
de-anonymize
remember that
the
well.
search data.
Yeah, we got
and it was a shit show. And as a result of that, all the companies stopped sharing data. So it was basically a 12-month period where you could do the work I did, and like internally, companies do it all the time, but externally, you can't get that data anymore.
But you also I feel like you named this really important phenomenon, right? Like, I think it's still, called this today. Like, it seems like there's a real skill in like you just nailed something that's so important.
So I have to confess that, yes, I mean, I did kind of come up with that name. It turns out that actually that phrase has been used before. People talk about fat tails, et cetera.
Fat tails is it? I heard it.
Yeah, it probably has been used, but I think I was at least invented in my own head, but I didn't think it was a big deal. And then it's like slide 7 in my presentation. And then I went to see Reed Hastings, the CEO of Netflix, and kind of walked through my presentation, walked through my analysis with him because they'd helped. And he got to slide 6 and he says, "There's your headline right there." And so Reed Hastings was the one who actually identified the long tail as being the sort of, the mot juste, if you will, that captured it.
Wow. And I guess it's funny. I feel like that's maybe the thing you're best known for. Are you kind of sick of talking about it, or
no? You know what? I'm not doing any active research in it, but no. I mean, what's interesting is that any sufficiently novel idea will separate the audience into two halves. There's those who say no way, and those who say duh. And it almost goes generationally. So anybody who grew up on the internet was like, duh, of course, lots of products, lots of choice, lots of, niches are a thing. And anybody who kind of grew up before that, and I don't mean to be ageist, but it's, kind of cultural age, if not chronological. There's a lot of people who grew up culturally in the era of blockbusters and top 40 radio and, three TV channels, et cetera, who basically, argued that the blockbuster was forever and that the long tail was a mirage that, probably wrongly gave hope to niche artists that they could somehow, work. And of course, they're right, and it was clear. I never said it was the end of the blockbuster. I said it was the end of the monopoly of the blockbuster. And I also, it was clear that the economic rewards would be felt largely by the aggregators rather than the creators. And, the cultural rewards are felt by all of us, of course. And the creators obviously, take music or writing or whatever. There's certainly some psychic rewards of being listened to or read. But you can't, the fact that the internet exists doesn't mean that a struggling musician is going to be any less struggling. So I think there's a lot of people who just kind of read it as only kind of blockbusters are dead, therefore the long tail is wrong. And they still say that. And then there's a lot of other people who feel that it's completely self-evident. One of the kind of tragedies is that I wrote the book before YouTube existed. And YouTube, of course, is the canonical long tail, marketplace of all kind of cultures and niches, et cetera. And so on one hand, it's kind of weird. I mean, I still have academics who sort of show me people really don't understand the math of the long tail. And they keep saying percentages. It's like, well, 1%, the top 1% of X still has 90% of and they don't realize that it's 1% of like 100 million. And so it's from, in absolute numbers is a lot, but still, and I still get this all the time from academics who long tail's a hoax because, top 1%, et cetera. Meanwhile, anybody who I should be able to say YouTube, discuss. But for some reason, some people just don't want to see it that way. So I do end up still trying to kind of find evidence of it. I mean, actually, it was a lot less controversial than my next book, Free, which was the economics of free stuff. And obviously, economics is largely focused on monetary economics, and yet there's obviously a non-monetary marketplace out there as well. I mean, we're doing it right now. You don't charge your listeners for this, and I don't charge you for this, and we're doing some exchange, some non-monetary exchange that has value, but economists don't know how to measure it.
Mm-hmm.
So that one was actually much more controversial.
Interesting. What was the controversy? Or like, did you feel like you got a lot of negative feedback?
Yeah, I mean, especially from media. I have a kind of a love-hate relationship with the media, which is increasingly becoming a hate-hate relationship. But the newspaper business was imploding, and they largely believed that the canonical error that the newspaper business made was putting their content free on the internet. And had they only set up paywalls at the beginning, that they somehow media would be preserved. And people in media take themselves pretty seriously. They feel like they're the fourth estate and protectors of democracy and the only people who can keep us from the mob, etc. And so they believed that free content on the internet was destroying this foundation of democracy, and that I was helping. I was not helping, if you will.
Okay, so what happened next? So then you got into drone.
Yeah, so running a magazine by day, but I still a nerd by night. And, so my first nerd thing was the long tail and the statistical analysis and, writing books. They were largely economic books because, I'm not trained in economics. My time at The Economist sort of osmotically, gave me some exposure. But still, basically I'm a programmer by heart. And as my kids got older, I've got 5 kids, and they were, my wife's a scientist as well, and we were trying to get them interested in science and technology. And so as they got older, I was thinking of, cool things to do with them. I actually started a site called Geek Dad, which is all about
Geek Dad? Wait,
yeah,
I know Geek Dad. That's awesome.
Yeah. Although I think Geek Mom is actually doing even better right now.
Nice.
Also a spin-off of this. But so I started Geek Dad, and it was largely the notion was, STEM projects that were sort of fun for the kid and fun for the adult, because there was a lot of things that were fun for the adult, not fun for the kid, or fun for the kid, not fun for the adult. But the ones that kind of got it exactly right. And so in the course of doing that, I was like, robots. We should probably do something with robots. And the kids are like, so we got so Lego. I was on their advisory board, and Lego sent me the first Lego Mindstorms.
Whoa, man, wow.
It was pretty
awesome.
cool.
Yeah.
So they sent me the first Lego Mindstorms, like beta testing, and so I showed it to the kids, and the kids are like, "Yeah, we'll do it." And so you follow the instruction to put together, and it takes all morning, and then you have a little sort of wheeled robot that'll kind of move towards a wall and then back away. Mm-hmm. And the kids are like, "You fucking kidding me?" No, sorry. They will definitely believe that. They do not use that kind of language. But internally, whatever the 9-year-old equivalent of that is. And I realized that, that Hollywood has ruined robotics for kids because you've got Transformers, and this incredible stuff. And meanwhile, real robots just don't, at least most of them don't really do anything. We're talking about Roomba, et cetera. So the sort of the gap between the sort of Hollywood version of robots and the prosaic reality was such that it was really hard to get them excited. Mm-hmm. So I thought, well, what would be cooler than a rolling robot? I thought a flying robot. Mm. And so I'm like, well, I don't actually know what a flying robot is. I'm just, I just Astro Boy or something. I'm not sure. So I literally Googled flying robot, and the first result was drone. I was like, I had thought about it. I guess a drone is a flying robot. Wait, what's a drone? So I Googled drone, and a drone is like a...
Wait, what year is this? This is like hard
this
to
is
imagine.
96, 97. Sorry, 2006, 2007.
Okay, wow. So drones are not in the zeitgeist yet.
No, well, drones were in the zeitgeist as a military thing.
I see. Right.
But there were no consumer drones. You couldn't buy one. I know. It seems so crazy now, but at the time it was like, drones were like a Predator that shot, Hellfire missiles, etc. It was really a purely military thing. Right. And so I Googled, so I'm like, what's a drone? And drone's like basically a plane with a brain. It had an autopilot. And I'm like, okay, wait, what's an autopilot? And you Google the autopilot, and it's like basically it's sensors and compute, and it's kind of figures out which way is down, which way is up, GPS, etc. And it's like those sensors and that compute. That's kind of what we have here in the Lego Mindstorms box, which came with accelerometer and magnetometer and gyro, etc. And I was like, let's just do it. And so around the dining room table, we built an autopilot out of Lego, stuck it in a radio-controlled airplane, and it kind of almost worked. And the kids thought that was mildly amusing for about, a minute. And I was blown away. I was like, what just happened? Did we really just build a drone with children on the dining room table out of Lego and it worked?
Wait, can I ask you a very just having messed around with drones quite a bit? I feel like you're skipping over the part where the thing keeps crashing and breaking, and then you spend like an hour putting it back together, and then it like crashes and breaks again.
Oh,
Like it's
oh,
maddening, right? Like
oh no, yeah. So I just told you the bit that got me excited. That put the idea in my brain. The next 5 years were just horrible. But I couldn't let it. So basically, what had happened in 2007 was a bunch of things that, in retrospect, seem obvious. But when 2007, it was the beginning of the maker movement. So it was 3D printing, it was Arduino came out. But what it really was the launch of the iPhone, 2007. So what's in an iPhone? A bunch of things, but including our MEMS sensors. These sensors that were chips, and previous sensors were mechanical. A gyro was literally a mechanical gyroscope, and it was just unaffordable, unattainable. And so I call this the peace dividend of the smartphone wars. But basically, the components of an iPhone had now been so cheap and available that you could then put them together in different ways and explore adjacent space. So like a Fitbit, well, the Wii controller, for example, was an accelerometer, a MEMS accelerometer. The Fitbit guys got a Wii controller, and just like I got Lego Mindstorms, said, what else could I do? They got a Wii controller, opened it up, saw the accelerometer, and thought, what else can we do? And they came up with Fitbit. And so there's a bunch of people who, were sort of looking at the components that came out of smartphones and thinking, how do I, recombine them to create something new and transform an industry? And so that's what we did. We basically, rather than drones which had been aerospace grade stuff, so you basically take an airplane, subtract the pilot, we're like, take a smartphone and add wings. And that bottoms up approach was completely radical and transformative, and was, initially was horrible. I mean, nothing worked. They crashed all the time. But because they were small and foam and cheap, nobody got hurt.
Right.
And because they were small and foam and cheap, we could actually build a community, and we got tens of thousands of people contributing and beta testing for all the right reasons. And we innovated. We collectively, as a community, innovated super fast, so that we went from, Lego to foam to plastic to basically dominating the drone world, including becoming the biggest drone producer in America, in North America, 5 years after that. Amazing. with no funding. That all just happened, and it just kind of exploded out of nowhere. It's kind of like the way the internet kind of took over the telecom sector, or PCs took over compute. This is a bunch of amateurs with open source software and hacked together stuff basically took over the future of aerospace. It was classic Gandhi stuff. First they ignored, then they laughed, then they fought, then they lost. And today it's pretty evident that the future of aerospace looks unmanned. It looks electric. It looks more like Silicon Valley than it does like Boeing or Airbus. Just like SpaceX did to the Launch Alliance. The tech, the Silicon Valley drone model seems to be the future of aviation everywhere.
That's so cool. And then wait, but and then how did you get into racing autonomous robots?
Right. So okay, I started with the hobby to industrialize my hobby. The drone community turns into a company. The company gets big, and now I'm running a company, which is all well and good. But again, still nerd, still wanting to get my hands dirty. Drones at this point, this is now 10 years on. So this is like, what year are we in? 20. So this is like 2017, 2000 or so. So at this point, drones are kind of a solved problem. It was really hard for a while, the Kalman filters and building robust, reliable systems, and connecting to the internet and the data payloads and the computer vision and all that kind of stuff. It was really hard for a while, but now it's kind of solved. And I'm always looking for some unsolved problem, something that's challenging. And you would think that drones as a 3D problem would be harder than cars, which are a 2D problem, but they're not. And the reason being is that you can get away with all sorts of slop up there in the air. The air is largely empty. You have GPS. And so, we didn't really care whether we were a meter off, or we were just basically we had GPS. We position and pose were kind of given to us. Position pose is given to us by the autopilot. It was hard to get there. a lot of work to figure out where down is in an inertial frame. And then position is given to us by GPS just for free.
Mhm.
So you can't assume that you have GPS with the car. You often don't. You need to establish position some other way. And also you need a kind of a level of precision that's like, centimeter or less, because there's lots of clutter, on the street. And so it's basically became a computer vision problem. So if drones were an inertial problem, basically, cars are a computer vision deep learning problem.
Mhm.
And, computer vision deep learning was just less advanced than classic control theory. So it was an opportunity to kind of go deep on computer vision and deep learning and, kind of get my brain going again. And once again, DIY drones led to an industry. So we're like, what should we call it? DIY Robocars. Because I don't know, we haven't figured out a name for autonomous cars yet. I went with Robocars. And let's do it again. This time, I'm not going to screw up my hobby by turning it into a company. I'm just going to leave it a hobby. But let's get this flywheel going again.
Mhm.
And once again, we had the enabling technologies, which were finally ready. We had good compute in forms like, we started with Raspberry Pi 3s and 4s, and then Jets and Nanos. The job is to keep it affordable, democratize the technology. So we put a limit
Totally.
of $400. Nothing
Mhm.
could cost more than $400. This is kind of what it looks like.
Oh, no way.
Yeah, this is a variant of it, but this is it's basically an RC car chassis with this one happens to be a Raspberry Pi 4 on the top,
Oh,
and
nice.
then a camera. This one also happens to have an Intel RealSense T265, which I'm playing with right now. But basically, that's all you need. You need a camera, you need a Raspberry Pi, you need an RC car.
Ooh, can I show you? I got one that well, this is not yours, but I made one that's kind of similar.
Yeah.
It's a Raspberry Pi 3 here.
Yeah.
With a camera, similar camera. I guess the chassis is a lot crappier than your chassis there.
Well, this one's actually not that good. I probably fiddled with it a lot. I added an encoder, a wheel encoder. So I'm the T65. Sorry to nerd out a little bit. The Intel RealSense T265 is a really interesting sensor. It gives you basically position. It's a visual SLAM, sensor, so it gives you position, but it's a lot better when it has an encoder. When it's matched with an encoder, it actually knows where it is. So it's doing it all visually with with an IMU and stereo vision, etc. And it's trying to it records what it sees and then records that as you follow a path and then tries to replicate it again, all visually. But it can tend to drift over time. So
can I see that sensor again?
It's this one right there.
So that's like two cameras.
It's two cameras and an IMU.
What's an IMU?
An inertial measurement unit. It's accelerometer. It's a combination of accelerometers, gyros, and a magnetometer that creates it gives you a position.
Gotcha.
So your phone has one in it. So this one's using a framework called Donkey, and so DIY Robocars is the community, but the actual project that is mostly used is called the Donkey Car. Okay. It's sort of, I would call it an MVP of self-driving cars. It's an end-to-end deep learning. And it works in the real world. It works in simulation, and the basic model is behavioral cloning. So what you do is you drive with a PlayStation controller. You drive it around a track, and it records the video, or the samples the video with stills as it goes around, and then matches those with the inputs from your controller. And so you now have a pair. You have basically, here's what the camera saw, and here's what the driver did, and you send them out to the cloud, and you run TensorFlow or whatever, fast AI or whatever you're using, and you come back with a model, an inference layer, and then the model runs locally. So we train in the cloud or on your PC. But then you create a model, then the model runs locally, and then you switch into auto mode, and then it drives by itself by simply sort of doing what you did, more or less, in the training session. So you can just drive around 3 or 4 laps, maybe go clockwise, counterclockwise, a little domain randomization, and it should learn how to drive. Now that's one technique. In the physical world, that's the easiest way to train it. In our virtual environment, in our simulator, you can use different methods. So there we use things like reinforcement learning, and we give it reward functions and and all that sort of thing, and where during COVID we've really pushed it towards simulation, and the exact same thing works. The exact same code works. It doesn't have to be on a physical car. Work on your laptop, and you're running in a Unity-based simulator. And so it's been a really good time for us to push hard on our simulation side of the equation. And one of the questions we'll have as COVID ends and we kind of return to physical races is how well do our models translate to the real world? Our sim
Yeah,
to real
always
gap.
a challenge. Yeah.
Exactly. And so we're working pretty closely with Unity right now to try to figure out how to improve the probability that our simulated created models will translate well. And so we're thinking a lot about domain randomization. And one thing it's hard to remember, but when this car, that camera is like 12 inches off the ground. Try putting your head 12 inches off the ground and try to see whether you can detect anything. And it's just, I mean, everything's so distorted and reflections and shadows, and it's really hard to see the world from there. And so what we're trying to do is we're trying to, simulators are too perfect. It's perfect information. We can create any level of resolution. They don't have motion blurs. So we're actually trying to kind of, to make the simulator worse. And like one of the problems we have here is that you'll train on the track and on your own it works great, and then during the race the crowd comes and now you have spectators all around the track, and now you have all these legs. And it completely throws off the model. And so we're actually modeling people and randomly putting people around the track to train the model to ignore that. And we're trying to figure out, what is it really looking at? Which color channel, what contrast, what do shadows do? And we're trying to understand better how to robustify the model to do the sim to real well.
Man, what a cool project. I have so many questions. Does the Unity, is it like in the scope of Unity? I should probably know this, but I really just don't. So I think of Unity as a graphics company. Does their engine also model physics?
They've really ramped up the robotics side. So you think of them as a game engine, and of course they're good at that. Competing with Unreal, they're kind of open source, and Unreal is less so, is not, I guess. But they're really pushing the robotics side, and yes, they use physics. So they use the NVIDIA physics engine in the background.
Cool.
And so it's quite good. And they have a whole team right now focused on robotics. They're initially focused on things like segmentation classification. So let's say, for example, you want to model a factory or a warehouse or the shelves of a 7-Eleven, et cetera. How do you identify an object, a carton of milk, occluded, rotated, bad lighting? How do you make sure you can identify it well? And so they focus a lot on that, just sort of taking objects and then sticking them in virtual environments and just making it, just creating a lot of noise and train the system to understand that. So that's they're also used a lot in full-size self-driving cars because they create beautiful photorealistic environments, and that's important as well. But what we're working on with them is video. I mean, yes, we screen grab the video, but the image moves. And so there's a correlation between the previous image and then the next image. So that includes things like motion blur, because our cars go really fast. They go probably 20, 30 miles an hour, but I mean scale speed is like 150 miles an hour, and when your camera's a foot off the ground, it is a lot of motion blur and things like that. So we're starting to model that. We procedurally generate tracks so that we can do domain randomization with tracks, make sure that we give the track certain parameters that at least don't break the physics. So one thing you could do is you could create a virtual model that can handle any track, but in the real world you've got things like physics, like the traction budget of your wheels, etc. So we have to model at least some physics so the tracks are realistic. And basically what you want to be able to, your training, you want to be able to sort of say, here's my model, here's my code, here's my hyperparameters, whatever. Stick it into the simulator, ideally in headless mode, so just running in the cloud. And I want you to run 1,000 iterations, and then I'm going to turn randomization on. So I want you to do 1,000 iterations of randomizing lighting, shadows, motion blur, objects that are surrounding, textures. I want you to go through randomize the courses as well. I want you to go clockwise and counterclockwise. I want you to change which track you're in at any point. Then I want you to add other cars that are also random. And so when you think about that, when you think about this sort of the industrial scale of just scenarios you can create, it gets really exciting. And so that's where Unity is focused right now.
Cool. What's your hope for this? Is it the joy of making something, or is there?
It's I mean, as you know, one of the rules of the maker movement is you never ask why, because the answer is always because we can. My personal thing is that it's just really engaging. It gives me a reason to explore, the cutting edge of machine learning and data science and things like that. So I need a reason. I'm like probably you. I can only learn by doing, and it gives me a reason to do it. As a community, our nominal reason is to democratize the technology. To basically, I don't have a real self-driving car. You probably don't have a real self-driving car, and that ain't right.
Man, well said. I love it.
So how do we make it so that more people can engage with self-driving cars without working for Google or Waymo or whatever? And the answer is you take the essence and you reduce it to a unit that anybody can have access to, exactly as we did with drones. I didn't have a Predator, so I made one out of Lego and foam. And I didn't have a self-driving car, so I made one out of toy parts and a Raspberry Pi. And so what you're seeing is this incredible diversity of people who are engaged. Last two we have our virtual races every month. 2 races ago, the number one winner was Japanese. I don't know what he does, but let's imagine just Japanese, engineer. Number 2 was French teenager. Number 3 was a 12-year-old Indian girl from Canada. And then down the line are, University of San Diego professors, retired people. It's just incredible diversity of people who can participate because if you do it virtually, it doesn't cost anything. It's just download some code and run it. And so we're really feeling like we're kind of, we're opening up the excitement of the industry to people who otherwise wouldn't have access to it. And some of them are doing it for fun. Some of them are doing it to get smart on, to have like a tangible reason to learn machine learning. And some of them are doing it because they want it to be their next career. And so we find we have a lot of people who are kind of mid-career. They're an engineer or whatever. They got a job, but it's not exciting for them. And this is super exciting. And so it gives them the chance to sort of fall in love with tech again.
And what are like the axes that you can change stuff, right? I think like one of the challenges of these simulations is it kind of constrains the hardware a bit, doesn't it? Or how do you think about that?
The axes that we don't really mess with are things like cost and danger. So we like to keep them small. We like to keep them cheap. Everything. So that's. There's some exceptions, and I can get into that later. But by and large, we want it should be something you can do indoors. It should be something that if it goes wrong, nobody gets hurt. So that's where we limit. Beyond that, the axes are really, there really aren't any constraints. So, for example, there are a lot of ways to do self-driving cars and a lot of sensors that are available. So one of the things that's gotten super interesting of late is that 2D lidar has gotten really cheap.
I have one of those, yeah.
And so you can get 2D lidar now for about $80 and a range of about 10 to 12 meters. So we can explore that. Right now we just use lidar for obstacle avoidance because our courses don't have a lot of structure. They're basically just white lines on carpet or on the pavement. I showed you the real sense sensors. This particular one was position, but they also have one that's depth sensing, which is useful for, again, obstacle avoidance.
Sorry, what is step sensing?
Depth sensing. Depth sensing. Forgive me. Another one is that we can actually go outdoors and use a drone autopilot on a car, and simply navigate by GPS alone. Now, GPS is not high enough resolution, but now RTK GPS, which uses a base station and a moving one, is quite affordable and can get you sort of centimeter level resolution. So this one here matches another GPS that's a base station that you have locally.
It's interesting, but you're not using any sonar anywhere, huh? Is it?
Sonar is really not useful
too unreliable?
For us. Yeah, so we used to use. There used to be something called the SparkFun Autonomous Vehicle Competition, which is no longer around, and that one was outdoors. And people originally used sonar to do things like avoid the hay bales on the side, etc.
Yeah, right.
Very, very noisy. So there is not a sensor that exists that we haven't explored. So yes, we had sonar. But then we would create sonar arrays
Whoa, cool.
of 360 degree sonar. Then we would of course the sonar is really old school, but the more recent ones are these time of flight sensors, these little tiny time of flight sensors. And so this one actually was just to compare sonar with time of flight sensing.
What's time of flight? Is that lidar?
It's like lidar. It shines a light beam out and then measures the time it takes to come back.
I see.
So basically, sonar is quite a wide beam and very noisy. It can, the environment can obstruct. Time of flight is much better and cheaper and smaller, etc. So
what about
we've tried it all.
radar?
We have radar as well. Radar is still relatively expensive. Also, radar it tends to be relatively broad beam, and that's not a problem. So it's, if you're in a full size car and you want to detect a car in front of you, it's fine for that. But we have other ways to do it, cheaper ways to do it, time of flight, for example. Because remember, our distances are like a couple meters, not tens of meters. So we don't have any need for radar because we can solve it with time of flight. Then we have solid state LiDAR, which again is affordable and mechanically a little simpler. We do a lot of crashing, so mechanical robustness is a good thing. There's of course, the nice thing about, the spinning LiDAR I just showed you is basically a 2D planar one. The solid state LiDAR has kind of a wedge shape, and so you get a little bit more structure that way. But again, the depth sensing cameras can give you much the same information, and they also give you sort of visual texture information, which is useful on top of that. I'm trying to think what other sensors we play with. Oh, there's a really smart one. So you can do a lot with cameras, and one of the winners uses, so most of these cameras, as you saw, are looking out, looking forward and a little bit down, and we're racing indoors. So what people realized is that if you know where you are on the track, you have a huge advantage because you know where the curves are. You can go fast on the straightaways and slow on the curves, and you can basically you have sort of foresight into what's going to happen. So how do you localize on a indoor track? And we have cones at the corners to detect when people are disqualified. And so people realized the cones were sort of a foot signature, of a fingerprint, if you will, for the track. And so they would use LiDAR to identify the cones. Now you can do it optically as well because the cones are orange. And so they would basically localize that. And then a genius guy named Andy Sloan realized that there's another fingerprint of the track of the course, which is that the lights on the ceiling had a distinctive pattern. And so his car actually has a fisheye lens. The camera looks up. It has a fisheye lens, and it can see around it a little bit, but it also sees the ceiling. And it basically just steers by looking at the lights above it, which is
and you don't consider
brilliant.
That cheating? You just, any way to hack your...
It works great indoors, but now we make them go outdoors as well.
I see.
And so it'll fail
Nice.
outdoors. And so what you need is, and then, as it happens, we do races in a place called Circuit Launch in Oakland near the airport. And they just renovated it during COVID, and they changed the lights. So... But yeah, so every trick you can think of, so it's called cone slam, by the way. Slam is simultaneous location mapping. So cone slam and light slam. And then anyway, I could go, down the rabbit hole, but I just wanted to say that we do racing, which is largely, about going fast and beating other people. But there's also ways to explore self-driving cars at a tiny scale in a sort of a city environment. And this is one cute version of it. Actually, I'm trying to remember what it's called. We'll put it in the show notes afterwards. But things like this use cameras and little Raspberry Pis, and it's called Zoomy. There, it just told me.
Nice.
And you can build a kind of a Lego-sized city with stop signs and street corners, etc. And so you can go to IKEA and get these like kids carpets that have cities for like toy cars, etc. And you could actually run one of these in it, and it'll navigate the city. So these things are super. They use Jupyter notebooks and Python, and they're really fun and easy and super cute. And you don't have to race to be able to participate.
Well, those eyes are so evocative too. I love it.
They are, yeah. It just said find Zoomy on your Wi-Fi, and then if you go there, it runs a little web server, and it's running a Jupyter notebook, and you can do things like drive in the town.
And so, what is the challenge to what are the people that are winning these things focused on? Is it like actually knowing your position and orientation really accurately, or is it like sort of strategizing your path through the course?
All of the above. It's things like racing lines, which is you find basically racing lines are the shortest path around the track, and going fast in the straightaways, and then braking at the right time. The classic racing stuff. Localization helps a lot. It allows you to create a strategy. Then then there's passing strategies and avoidance strategies, and how do you win when you're going head to head, as they always are.
Is drafting relevant at these low speeds?
No, it's not. It's not. Yeah, I mean, they're going 20 miles an hour, but they're small. Sure. Biggest challenge, though, and this is one that does not show up a lot in self-driving in real self-driving cars, is we're going freaking fast. So 20 miles an hour in a 1/10 car. That's 200 miles an hour, and so this is real-time robotics. And I don't know how much you've spent with real-time robotics, but 20 milliseconds is slow. And so our inner loops, we could be running them at 1,000 hertz.
Mm-hmm. Well, so you do inference at 20 milliseconds on a Raspberry Pi 3? That
Depends.
seems...
So obviously we lower the. So no, we're not doing inference at 20 milliseconds on a Raspberry Pi 3, but we can do 100 milliseconds on a Raspberry Pi 4.
Right.
And that's your sort of your AI loop. Then you might have a motor controller loop that's running faster. If you're running an IMU, etc., you might be detecting the IMUs, which is again the inertial measurements, would be detecting something like drifting. So if you're supposed to be going straight and you actually have some lateral movement, that means that your wheels, your tires have lost traction and you're skidding. So how do we do real time? And the answer is, so you need at least I would say 30 frames per second, at least 30 frames a second. That's actually real cars are not sampling that fast. And if you're going 30 frames a second, you may have to make some concessions. So first of all, our cameras are relatively low res.
Mm-hmm.
So we're running at like 320. And our models are pretty simplified. We might have 3 or 4 layers, but no more than that. We're not running a lot of models simultaneously, so it's end-to-end neural network. So basically, it's just pixels come in and commands to the steering go out.
Mm-hmm.
So we're not running parallel networks, etc. But yeah, these are all great challenges. If you tell somebody, keep it under $400 and win,
mm-hmm.
it requires a lot of creative thinking about that, and you can't just throw compute at it.
Right.
It's not okay to show up with the kind of stuff you'll find in the trunk of a Waymo. That's cheating. You show up with your Jetson Nano or your Raspberry Pi 4, and then you use some creative algorithm or technique to win, and that's the fun.
Yeah, that is so fun. I mean, Jetson Nano or even Raspberry Pi 4 is no joke these days, though. It's funny to me. It's just like, this is amazing, like what we can do.
Yeah, it's they're both like, I don't know, the Nano right now is like $60 or something. The 2 gigabyte one, and the Raspberry Pi 4 is about the same. So it's really great. But what's really important is the software frameworks now support them. So TensorRT, TensorFlow RT, Keras, FastAI, they're all starting to think about edge compute. And so
I just want to say they've put in so much effort and they're so friendly. Like, I feel like when I've asked questions, they've just been unbelievably helpful. So I don't know. I feel like I need to just give them a thank you for that.
Absolutely. And, and everyone's doing it. So NVIDIA's, obviously they didn't have to come out with a Jetson that cost $59, but they did. Amazon's set up a RoboMaker, which is their, virtual environment for this. Microsoft is investing a huge amount into edge AI. Intel, the Intel RealSense I just told you about, Raspberry Pi, et cetera. All the Google stuff is focused on edge AI as well. So the notion that the edge, so the cloud and the core is one thing, but the edge is completely different in that you have real world inputs, real time inputs, real time outputs, and they tend to be small, cheap, power efficient, et cetera. And so, you realize that the internet has always been this way, that it's a combination of the edge and the core, and that, it shifts. Where's the thinking done? Where's the intelligence? And it's got to be some balance. And, we got the cloud, we got the core down right, but the edge is an opportunity to basically pre-process a lot of data before you get it. Because we can gather so much data. If we can pre-process it with deep learning in the edge, it actually makes the core smarter as well.
Totally.
So it's really exciting what's happening right now, both not only with deep learning, but also computer vision. I'm a big fan of a project called OpenMV, which is basically, it looks just like one of these cameras, actually. So we've been talking a lot about deep learning, but computer vision is equally exciting. This is an OpenMV, and it's basically, again, a $50 board, but it's a camera, and it's got compute on board, and it's basically running OpenCV, and it runs it really well with the Python interface, a fantastic IDE. And you basically just stick this on anything. It's got it can run a car just all by itself, and now you've got the stuff that was like a PhD 10 years ago of edge detection and some simple deep learning networks, object detection, all sorts of transforms, etc., all just already built into this thing. And any kid can now use this to do sophisticated computer vision. And so actually cars that use nothing more than this have consistently scored in the top 10.
Wow.
And you could stick this, I mean, you can literally make a self-driving racing car for less than $100 with something like this.
So cool. So, I mean, before I let you go, I'd love to ask you a couple broader questions. And, I think one that I think you watched the Peter Norvig episode, and I was really kind of curious to ask him this. And you're here too as like someone who's kind of been watching machine learning for like, longer than most. And I'm really curious what your perspective is, like having sort of seen like a long arc of this stuff. I guess everyone must ask these questions, so I feel a little shy asking them, but I'm really curious what you think, right? When do you think we'll see, like, for example, like autonomous cars, like working in our life at all times? And kind of where do you think this goes? Like, do you feel like there's probably fundamental limitations to what we're doing with neural networks now? Or do you feel like, just kind of scaling up what we have leads to singularity like outcomes?
Everything I know about deep learning, I probably learned from listening to your podcast. I mean, because I'm dabbling. Peter Norvig's a legend, but
But you were training neural nets like back in grad school, no?
Yeah, but they weren't. These were Hopfield nets, and we hadn't really figured out the whole notion of layers and convolution and all that kind of stuff. So they didn't. There was a real dead end, and it was very frustrating. So I with drones. Once we got one drone to fly, I was like, sky's going to be dark with these things. They're essentially free. They're it's done. Let's just, I mean, why do we think of how great it would be to have, total information awareness of our planet. To be able to, rather than waiting for the satellites to come by or for the clouds to clear or having, cameras on every stoplight, what if we could just sort of, have a camera anywhere, anytime to measure our planet so we could manage it better? So it seemed to me obvious that the missing middle, if you will, we had cameras on the ground and we had cameras in space, and the missing middle was the air, which is, an opportunity to be anywhere, anytime, higher resolution. Just seemed like a good thing to instrument our planet. And yet here we are. There's nothing in the air. I can't believe it. It's been like 15 years and we still don't have sky dark with these things. We really don't have any autonomous drones at all in operation, except for the military, like we had back then. So what happened? Well, the problem wasn't technical. The problem was regulatory. It is the FAA will not allow drones to fly beyond visual line of sight. Won't allow them to fly without a one-to-one pilot, like with sticks, like an animal. Basically, the FAA will not allow drones to be autonomous. It won't allow drones to be, us to break the one-to-one ratio, which we've achieved nothing in a sense. Imagine a robot that could only work teleoperated. I mean, what have you achieved? You still have one person, one robot, and that's where we are. Drones are essentially have to be teleoperated, or at least have someone monitoring autonomous operations, which is even worse because now they're not doing anything. So that was disappointing. It was disappointing for a regulatory reason, and I can understand it, and I work with the FAA pretty closely on trying to resolve it. But, the question about cars is also it's more about society and regulation than it is about the cars. Can cars be autonomous today? Yes. Can they be autonomous everywhere perfectly? No. Should it be okay for cars to be deployed autonomously in some places where they can be highly reliable, but not everywhere? Absolutely. And companies like Voyage are doing that with retirement communities, closed courses, if you will. So I think the question is, so are drones in use today autonomously? Yes. Are they overhead right now? No. Am I disappointed there aren't more of them? Yes. But, obviously they go where they're needed most. And I presume that self-driving cars, I think we're setting the wrong standard. Should we have, self-driving Ubers, in all cities? Probably not. There's not a lot of advantage to it. Waymo's doing a little bit in Arizona, but that's probably not a game changer. Where would self-driving cars be a game changer? I think actually retirement communities are a really good example. They're quite empowering and liberating for people. And so I think if you sort of reset and say, as the technology gets better, will we identify really useful places where it wants to be, and and focus less on the tech and more about the marketplaces and the demand? Will we find those places? And the answer is yes. And so I think that all the questions about when are self-driving cars come, they all kind of come from a technology place. And I think I think we're being Silicon Valley, we're in our Silicon Valley bubble. We really need to understand the needs, the use cases, the places that would benefit most from them, and think less about the tech and more about how it's going to be used.
Interesting perspective. Thanks. So there's sort of two questions that we always end with, and the second to last one is, From your perspective, especially from drones and robots, what's one underrated aspect of machine learning that you think people should pay more attention to?
I think I mentioned I'm really into simulation and synthetic data, and I know you had a couple episodes now on synthetic data creation. But I do think this is the golden age of simulation. I work really closely with Microsoft, and if you've used Microsoft Flight Simulator 2020, which basically uses satellite and aerial data to recreate the entire planet at photorealistically, with using photogrammetry to kind of create a 3D models of the planet, but I mean, like real time, like with weather and everything, like as it really is. I think this is the golden age of simulation, the golden age of rendering that. And as a result, our opportunity to use these powerful engines to train models better. We talked about domain randomization. We talked about synthetic data, but I'm most excited about that, because I feel like we've kind of hit some limits in the ability of humans to train models, and even CPT 3 is limited by as you've mentioned before, is limited by the amount of data on the internet, which sounds like a lot, but is never enough. And so I think that we need to start generating. We need to think really hard about our synthetic data generation strategies so that we can, break through the limits of real data and start training them on things that we can only imagine.
Totally. Okay, and then final question is for you, and you've actually built a pretty sophisticated end-to-end ML system now. What's like the biggest challenge of getting that to work, or what's the challenge of getting that to work that people might not expect when you just sort of lay out what you're doing?
So first of all, I should say I did not build this. This is the Donkey Car team, and there's a lot of people there who get credit for that. Ton Kramer was the originator of the current stack. So first of all, one thing you should know about end to end is that it is end to end. All we have is one channel, right? Pictures come in and controls go out. We're blessed to have things like TensorFlow that will do that. But once we start introducing other things like depth sensing and those other sensors we talk about, we're probably going to need to introduce multiple parallel networks, running. Now, should the obstacle avoidance be also running on machine learning, or should that be more sort of classical control theory, like if then, if you will? How do we combine classic robotics control theory with deep learning? One's probabilistic, the other one's deterministic. How do we merge them? And so I think there's some interesting work to do to start to introduce multiple inputs. Right now we have one input, one output, but of course, in robotics, it's MIMO, multiple input, multiple output. And I think, if you stick to the $400 limit to be able to do multiple input, multiple output with deep learning, in all of these channels is super interesting. I don't know whether we're there yet, but that's sort of, you asked what have we learned, and we've learned that you can do one channel, one network pretty easily, and it works amazingly well, but it doesn't scale to multiple inputs. And if you really want to start like winning against competitive races with other cars and actually doing what a human would do in a race, we're going to need to bring in all the channels and sensors and data we can, and that means a different architecture.
Although the part of that car that's going to come down is the running neural networks, right? I mean, I feel like that's the thing that seems to be dropping the fastest.
That is good news. The Raspberry Pi 5 or the Xavier Jetson can do that. Then maybe we can just apply our same technique and just say, okay, let's add another network to keep track of the other cars, add a third network to keep track of the sliding, the friction, how the car is actually mechanically moving on the track with the IMU, and then, find some way to merge them. That would be super exciting. I don't, to do the whole thing at 30, 50, 60 frames per second, under $400, I don't think we're quite there yet, but you're right. That's going to be the focus over the next couple of years.
Awesome. Well, thanks so much. It's an honor to talk to you, and that was so much fun.
This was a pleasure.
Thanks for listening to another episode of Gradient Descent. Doing these interviews are a lot of fun, and it's especially fun for me when I can actually hear from the people that are listening to the episodes. So if you wouldn't mind leaving a comment and telling me what you think or starting a conversation, that would make me inspired to do more of these episodes. And also, if you wouldn't mind liking and subscribing, I'd appreciate that a lot.